Hi, welcome to another video tutorial in which we are going through the Andrews lectures on how to build large language models. To continue, in the last lecture, we saw how can we differentiate a function uh, through backpropagation and update the weights so that the loss gets to minimum. So this was a high-level example to walk you through how differentiation works. Now, in the real world, we can create these networks in a very different fashion, in very different ways. So the core of the neural networks is basically the inputs that we have, we're going to multiply it with some weights. So by multiplication, it can't necessarily be multiplication. It can be any sort of mathematical operation. It can be simple or complex. And then we're going to look at the output. Now come back and readjust these weights and perform the same mathematical calculation. And again, check how is the performance with the new output. So in this process, the only thing that we need to make sure is we need to create this mathematical formulas or calculation in such a way that these equations must be differentiable. So, in the previous example, we saw a basic methodology where we just multiply and add weights or values and then get to some output. So in this lecture, we are going to increase the complexity a little more because we're going to increase the complexity a little more and add activation functions. What are activation functions? They simply are another kind of mathematical expression that somehow works well when clubbed together in the neural network. So just like we have multiplication and addition, there is also activation function, which is a mathematical representation of the network where it turns the data to a non-linearity. What do we mean by that? So if we look at our previous example, the basic example, we're just going to multiply and add. So this is just a linear combination of sequences that are happening. So in order to get into complex neural networks, if this is just a linear combination, the output will never converge because the real world data will be non-linear, right? So what do I mean by non-linear in the real world? So the graph that we are seeing here, this is not how a real world loss looks like. The real world loss looks very nonlinear. So is this plot is drawn on one weight value, right? And in the real world or in the huge neural network, we'll have thousands of weights. So we'll have 1,000 dimensions. And imagine this curve to be in this 1,000 dimension space. And this curve won't have a local minima. That means there won't be one single set of, there will be, but there won't be only a single set of weights at which the loss is lowest. It can have different weight values at which the loss can be less or low. Hence, in the real world, we won't be having a local minimum. That means, but we will have global minima and global maxima. The goal of the neural networks is not to reach to local minima. The goal of the neural networks is no matter at which random value of weight you start with, just keep iterating through until you reach the local minima of the loss. So maybe I can better illustrate this with a picture that I'm going to draw real quick. So this is a 2-dimension, and let's assume this is a 3-dimension picture, or let's assume this plot to be a 3-dimensional one, and our loss might be something like this, right? So if we initiate our weights, so this is a multi-dimensional thing, but if we initiate our weights at this point, then the first iteration loss is going to be here, and then as we keep iterating or as we keep differentiating, the lowest point that we reach is here. So this is local minimum, and this can be a global minimum. At least with the picture that I have drawn, this is the global minimum. So this is where our neural networks try to reach by changing the value. So the weight starts from W1 here and might end at WX. So this is a new weight value, and this is the loss, right? Hence, in order to reach from here to there, we need to have differentiation functions in our mathematical equation, and we essentially can have any differentiation values in there, any mathematical equations that are differentiable. So going back to our lecture today, one of the differential equation that I would like to talk is activation function. They basically add non-linearity to our linear multiplications so that it enhances the properties of neural network. This is the one little one of the research aspects that many people have worked on and came up with activation functions. So it's one type of mathematical squeezing or calculation performed in order to make sure that we get a reliable output. We slowly go to a reliable output. One of the mathematical functions is tan h. So a tan h has a very distinctive properties. It basically has any value below. It has a min and max of 0 and 1, and anything that has greater or less than a specific threshold, they'll have either -1 or 1. And anything in between this range will have some value between 0 and 1. And at 0, the tan h value is essentially 0. So, so this is the representation of the mathematical calculation that we'll actually perform in neural networks. We'll take the inputs, that is x0, x1, x2, and we'll create the weights w0, w1, w2, which multiply the input with respect to the weight, and then add some bias to it. Okay, we can talk about this later, but basically this is one type of calculation that we do. So again, if we look at its core, it's just multiplying input with weight and then adding some bias. So that means this is more or less like a linear operation for all the inputs and weights. This is not something that we are just directly going to use it for calculating the output. We're going to add one layer of complexity here, saying, hey, once you have the output from this calculation or multiplication, let's pass it through an activation function. An activation function, something like tan h, essentially outputs whatever values that we get. If we get the sum of wx plus b to be 5, then the tan h of 5 could be something near to 1. If we get wx plus b to be 2.2 or to be 1, then the output will be 0.75. So in this way, an activation function adds non-linearity to a sequence, and that proved to be effective in building neural networks. So this is the activation function, and let me actually start. So now let's continue on building a neural network, a very basic neural network. So we can start off by actually, I'm pasting the values here, where x1 and x2 are inputs, right? x1 and x2. And then we have weights, which are w1 and w2. So these are used to multiply with the inputs. And along with that, we have a bias known as, which we add to the equation. So in order to see how these values are changing, it's good to keep track of every calculation that we perform so that we can easily visualize it in the graph. So this is the x1 times w1, and as well as x2 times w2, right? And now this is actually x1 times w1 plus x1 times w2, and then we are also adding bias, so plus b, that is equals to n. That is basically broken down in different values. And now if we just draw n, so we just gave the calculation, we labeled it, and so this is x1 w1 x2 w2, and this is n, which is x1 w1 x2 w2 plus b. So if I just draw this, we can see that x1 x2 w1 w2 are multiplied to give x1 w1 and x2 w2. Then we are adding x1 w1 and x2 w2 with the addition symbol, and then later on adding bias to it. So now this is just a normal equation like we did in the past, where we multiplied and added. So the complexity that we're going to add, that we're going to append, or the layer that you're going to add here, is basically a tanh function. So before before going to n, let's add another layer here known as tanh function. So why tanh? Or we can essentially use any type of activation function. Tanh is one of the easiest one to implement, and it is pretty widely used as well. We will go into different type of activation functions in the future, but basically tanh equation, so it's a hyperbolic tangent. That means it has exponential properties. So if an equation is exponential, then that means it can be differentiable. Hence, we can leverage tanh to create an activation function. So this is the equation of tanh, e to the power 2x minus 1 by e to the power 2x plus 1. So in order to add tanh here, we need to actually add this as a function, because just like addition and multiplication, we are going to do tanh operation. Hence, we need to add to our basic function or class the tanh information. So we can define tanh as, so we will get, so whenever we call this tanh, we're going to pass our value as an input. So that is, let's save this as x. Now, what are we trying to share here? We are trying to create this formula of tanh e to the power of 2x minus 1 divided by e to the power of 2x plus 1. In order to just implement this formula, we can leverage math.exponential of 2 to the power x. So we have e to the power of 2x. Yep, e to the power of 2x, which is a numerator. And then we're going to do minus 1. This is our numerator. And just like that, we're going to at the denominator where it will be e to the power. So e to the power of 2x plus 1. So this, let's suppose throw it in a variable t, and this is the value of whatever input that we give. This is the tan h value of it. Now, since we want to visualize this in the graph, we would like to place that in a value class with data that is t, right, and then children. So since it basically does not have any children, and we can just do it as self. It doesn't have it's just a single tuple, and then the label that we could do is, I mean, we can skip on the label. Let's leave it blank for now. But the operation that we can do, oh no, sorry. So the label is basically tan h, right? The operation is something that we'll skip because it's not straightforward to represent. But or we can type it as activation function, right? And just putting it out. And once this is done, we're gonna return the output. Now we can say that now we need to update this such that output O, that is equals to n dot tan h, right? N is the value that we have, like this is the n, and we're adding another value, an activation function here, which will give an output O here. So now, since we did that, and let's say O dot label is output O. Okay, so we have okay, data dot self. I think we have data. Yeah, we have data here. So let me pause on this. Yeah, sorry. It's such a rookie mistake. Yeah, this is a beginner mistake. So we do self.data. And now we can see that after n, we are passing it through some activation function, and the output is 0.644. So 0.7, which is somewhere around here, maybe has an output of 0.644, somewhere around here. So that's the output that we are seeing. So in this way, we added one more layer of complexity to our neural network. Instead of addition and multiplication, we have added a nonlinear function, which in this example is a tan h activation function. Cool. Now how? This is a forward propagation. Now we need to calculate the backward propagation in order to know how much of a weight change should be for each of the nodes or inputs. So we will go through the backpropagation. And in order to do that, there is one special element that is really important, or that makes basically a whole equations easier to calculate, is by having some constant bias 6.88. So yeah, now we can see that start backpropagation, and on step 1 is to do do by do, which is equals to 1. So that means O dot grad is equals to 1, right? So the gradient with which you have to change O is 1. Now let's see. Let's come a step back, and basically O is tan h of n, right? Because once we have n, we are passing it through tan h, and then that's resulting O. So this is O is equals to tan H of n. Now dO, how much is O changing with respect to n, is equals to how much? So we need to find the differentiation equation for this. Again, there are two methods. One is you nudge your n by a small margin, nudge your x by a small margin, and see how much of a change it is to calculate the derivative. Or you can simply look out for the differentiation equation for tan h. So if we look at the differentiation equations, derivatives, we can clearly see that derivative of tan h is 1 minus tan h square or sec x or 1 by cos x square. So the easiest one here we have is 1 minus tan h square, because O is, or yeah, so because O is basically tan h. So 1 minus tan h of n square. So what are we doing? We are basically saying O is equals to, 1 minus tan h of n square. And yes, so this is the differentiation of dO by dN. So basically that means 1 minus tan h of n is basically O, so O squared. So this is dO by dN. And now calculating this value will be 1 minus O dot data whole square. So that is 0.5. Hence, the n dot grad is equals to 0.5. Right? I hope you're following me here. O is, so the differentiation of tan h is basically 1 minus tan h square. And since tan h of n is O, so we're going to do 1 minus O square, that is 0.5. Simple. So we got n dot grad. Once this is done, we need to take a step back. And if we recall from our previous lectures, when we have summation in between, the derivative just goes a layer back. Or so that means whatever gradient n has, it will be same for these two nodes, or for this bias and weights, for this bias and calculation, because there's a positive symbol here, right? So next, if I do x1 w1 x2 w2 dot gradient is equals to 0.5, since there is plus sign and n has gradient of 0.5. In the same way, we have b dot grad, which is equals to 0.5, right? So let me stop here and execute this so that we can see how far we came along. Okay, n dot, why do we have, okay, we are just replacing it, so I should probably do this. So we can see the gradient of O by O is 1, gradient of O with respect to n, where our activation function is tan h, is 0.5. And then we have the gradients coming a layer back because of positive symbol. And now it again goes back to the same thing here. So since there's a positive sign, we can do x2 w2 dot grad is equals to 0.5, and then x1 w1 dot grad is equals to 0.5. right? Cool. So we got it till here. Now it's time to go a step back. In order to do, now there's a multiplication factor here, and if you recall our previous videos, the way we differentiate in a when there's a multiplication is a little tricky, but basically we're going to take for W2, we're going to take the data of X2 and then we're going to multiply it with the gradient of X2 W2. So let me write it down for you. So W2 dot graph is basically equals to X2 dot data, the value of X2, into X2 W2 dot gradient, right? Which is 0.5. We can write that, or we can just leave it as it is. So yeah. So in the same way, if we want to do it for X2 dot gradient is equals to W2 dot data into X2 W2 dot gradient. So if you look close at this specific X2 and W2, the value of X2 is actually 0. That means the input, it has value 0, and hence when you multiply the input with respect to the weight, your output is also going to be 0. Because of this, the gradient that you calculate for W2, that is the weight, is going to be 0. Now W2 dot graph, yeah, so the weight of W2 is 0. So what this means is if you have any input that is 0 and there's a multiplication aspect, then the weight that you create for this input is also going to be 0. Since there is no value there from which it can learn, that's the reason why mathematically even the weights and the gradients become 0 after one iteration. Pretty cool stuff, right? So now let's calculate for W1 dot grad is equals to X1 dot data. So whatever present here multiplied with this gradient 0.5 into X1 W1 dot gradient, and X1 dot gradient is equals to W1 dot data into X1 W1 dot gradient, right? And now I could see that at -3 into 0.5 yielded minus 1.5 gradient, and 2 into 0.5 yielded 1, and 1 into 0.5 yielded 0.5, but 0 into 0 yielded 0, 0 into 0.5 yielded 0. So after one iteration, the X2 W2 will also go back to 0. So in this way, we did one back propagation by taking inputs X1, X2, multiplying them with weights W1, W2, and next we did some operations. Just like multiplication, we added the bias, and then we added all of this X1, X into W plus B, which is the activation which is basically what goes before an activation function. And once that is done, we just passed it through an activation function tanh, and then calculated the gradients. So this is how we can add a layer of complexity into the neural network by creating nonlinear patterns with the activation function. In the next lecture, so all of this is one back propagation, And in the next lecture, he'll find automatic ways to basically iterate this over many iterations and loops. Thank you for staying on this. I hope you had a pleasant time learning along with me. And in case of any questions, feel free to contact me. Thank you for your time. Take care. Bye.